Ever had that moment when you're holding something icy cold and you start to wonder, what exactly is coldness anyway?
Mm.
Or maybe you've noticed your phone getting warm in your pocket and thought about, all that energy at work.
Yeah, it happens all the time.
These everyday puzzles actually point to some incredibly fundamental principles governing energy and temperature. And that's precisely what we're diving into today.
You've given us a fantastic collection of material exploring the fascinating world of thermodynamics. I mean, from the tiniest movements of particles
Right.
to the massive power of heat engines and the way heat flows all around us. It's a huge topic.
It really is.
But our goal today is, I guess, to extract the most crucial and captivating insights without getting too bogged down in, overwhelming detail.
Exactly. Think of this as your express route to understanding the core ideas.
Uh,
What thermal energy really is, how temperature fits in, and the big laws that dictate how it all works.
Mm.
We've got definitions, the connections between these key players, and some genuinely surprising ways these concepts show up in the real world. Okay, so to get us started, what's the absolute bedrock here? Beyond just feeling hot or cold, what's the underlying science?
Well, at its core, we really need to differentiate between thermal energy and internal energy.
Okay.
Thermal energy, ETH, specifically refers to the energy associated with the random motion of particles within matter.
Random motion.
Yeah, translation, rotation, vibration,
Yeah.
all that jiggling around. Now, if those particles are moving together in a coordinated way, that doesn't count as thermal energy.
Ah.
Internal energy, that's the bigger picture. It includes all that thermal energy, sure, but also other forms of energy stored within those particles like, chemical bond energy, nuclear energy.
Got it. So when you talk about heat, it's not something an object has, right? It's more about an action, something happening.
Exactly. Heat is defined as the transfer of thermal energy from one system to another. It's energy in transit.
Only in transit.
Only in transit. And only because of a temperature difference.
Right.
And yeah, to heat something just means to increase its temperature.
Right.
Now, temperature itself, T, it's directly linked to this internal jostling. Higher temperature means particles have more random motion, higher thermal energy,
And lower means less?
and vice versa. Yeah. So simply put, hotter objects have a higher temperature, more thermal energy at the particle level.
That makes sense. It's all about that microscopic activity. Now, one of the things that caught my eye in the material was the ideal gas thermometer. What makes that such a, fundamental tool?
Yeah. What's fascinating there is that the ideal gas thermometer works based on really fundamental principles. An ideal gas is, it's a theoretical model,
Right, perfect world kind of thing.
pretty much. Tiny particles, elastic collisions, negligible volume. The key insight is, if you take a fixed volume of this ideal gas and heat it, the pressure goes up in direct proportion to its absolute temperature.
Yeah.
So the thermometer uses that. You measure the pressure, maybe by looking at a liquid column, and that gives you a really accurate measure of the absolute temperature.
Okay, so we've got thermal energy as the jiggling, internal energy as the total stored energy, heat as the movement of that jiggling energy, and temperature as a way to measure how intense that jiggling is. Now, when we're describing a system using thermodynamics, what are the key things we need to know? The material mentioned thermodynamic state variables.
Right, these are the essentials that define the condition or state of a system.
Yeah.
The main ones are pressure, P, volume, V, temperature, T, and the amount of substance, usually the number of moles, N.
PVTN. Got it.
And what's really important about these state variables is that their values depend only on the current state of the system, not how it got there.
Okay, so the history doesn't matter.
Not for state variables, no.
Yeah.
Whether you heated a gas quickly or slowly to reach a certain T and V, its pressure at that moment will be the same. And things derive from them, like internal energy and entropy, which we'll get to, they're state variables too.
Right, it's all about the here and now, not the journey. Okay, now we all use Celsius and Fahrenheit, day to day, but there are these other temperature scales. What's the story there?
You're right. Celsius and Fahrenheit are what we call arbitrary scales. Their definitions are based on specific sort of convenient points, usually water.
Freezing and boiling.
Exactly. Celsius sets 0 degrees C near freezing, 100 degrees C near boiling. It's standard pressure. Absolute zero is minus 273.15 degrees C. Fahrenheit uses 32 degrees FOA and 212 degrees for water, and absolute zero is way down at minus 459.67 degrees Eiffel.
And those absolute zero values are significant because...
Absolute zero is the theoretical point where matter has the minimum possible thermal energy. No more jiggling, essentially.
Okay.
And that leads us to the absolute temperature scales.
Yeah.
Kelvin and Rankine. Kelvin is crucial in science. It says 0K is absolute zero.
That starts at the bottom.
Exactly. And critically, a change of 1 Kelvin is exactly the same size as a change of 1 degree Celsius. We also don't use a degree symbol with Kelvin, just K.
Ah, right, just K.
Then there's Rankine, which is like Kelvin but uses the Fahrenheit degree size. 0 degree R is also absolute zero. But interestingly, NIST, the standards agency, actually recommends against using Rankine these days.
Huh. Okay, so Kelvin is king in science. It's like Celsius shifted down.
Pretty much. And Rankine is the Fahrenheit equivalent, though less used. The material also gave us those conversion formulas.
Yeah, those are handy. Let's quickly recap Celsius to Fahrenheit.
T degree is 95 T degrees plus 32.
And Fahrenheit back to Celsius.
That's T degrees C plus 273.15.
Okay. And Kelvin?
Simple one. TK, T degrees C plus 273.15.
And Rankine from Fahrenheit.
T degrees R plus 459.67.
And Kelvin to Rankine, just in case.
TK, 59 T degrees.
Good to have those. Okay, let's talk about describing system properties. I saw extensive and intensive. What's the difference?
Yeah, that's a really fundamental distinction. Extensive properties depend on the amount or size of the system.
Like mass or volume.
Exactly. Double the stuff, you double the volume, double the mass. Those are extensive. Intensive properties, on the other hand, are independent of the size. Temperature, pressure, density. If you take a sample, those properties don't change just because you took a sample. Got it. Size matters for extensive, doesn't for intensive. Okay. We also saw moles and Avogadro's number. Feels a bit like chemistry class sneaking in.
Yeah, there's definitely overlap. The mole is basically just a chemist's dozen, but a really, really big one. It's a way to count huge numbers of tiny particles, atoms, molecules.
How huge.
1 mole is exactly 6.022 times 10 to the 23rd particles. That number is Avogadro's number.
Wow.
It's useful because it connects the microscopic world to the macroscopic one we measure. Like, 1 mole of carbon-12 atoms has a mass of exactly 12 grams.
Okay.
So molar mass is the mass of 1 mole, usually grams per mole. And the total mass is just molar mass times the number of moles. And simple relationship, molar volume is just the volume of 1 mole. Makes handling those crazy big numbers of particles a bit easier. So we've set the stage. Energy, temperature, describing systems. Now for the big ones, right? The laws of thermodynamics. Where do we start?
Right, the laws. These are the fundamental rules of the game for energy and matter. We actually start with the zeroth law.
Zeroth? Why not first?
Good question. It was formulated after the first and second, but it's considered more fundamental logically. It establishes thermal equilibrium.
Okay, what does it say?
It says if system A is in thermal equilibrium with system C, and system B is also in thermal equilibrium with C.
Then A and B must be in equilibrium with each other.
Exactly.
Yeah.
It sounds obvious, but it's the basis for why temperature measurements work. It means things in equilibrium have the same temperature. It allows thermometers to make sense.
So it's the logic behind comparing temperatures.
All right.
Okay, what's next? First law.
Yep, first law. This one's pretty straightforward. It's conservation of energy.
Energy can't be created or destroyed.
Precisely. For any thermodynamic system, the change in its internal energy, that's AU, equals the heat added to the system, Q, minus the work done by the system, W. So UU equal QW.
Energy in as heat minus energy out as work equals the change in stored energy.
You got it. Energy is accounted for. It just changes form or location.
Seems fundamental enough. And then the second law. This is the one that always feels a bit more mysterious.
The second law is definitely profound. It introduces entropy. Now, entropy is often described as like disorder or randomness.
Yeah, that's what I usually hear. Things getting messy.
Right. But a more precise way to think about it, maybe more useful, is as a measure of how much of a system's thermal energy is unavailable to do useful work at a given temperature. Or, conversely, how spread out the energy is.
Unavailable. So high entropy is bad for getting work done.
Not exactly. It's a bit counterintuitive. Entropy is a state variable, depends only on the current state. We can calculate changes in it, but can't measure it directly like temperature. And it's extensive at entropies together. But here's the key bit. A system with higher entropy actually holds energy in a way that might require more careful extraction to do work, but it isn't necessarily less potential. Think of it as energy being spread among more possibilities, more microstates. High entropy means lots of ways for the energy to be arranged internally.
Okay, so it's not just simple disorder is useless.
It's more nuanced. Increased entropy often corresponds to energy becoming more dispersed, less concentrated, which makes directed work harder, but the potential isn't gone, just spread out.
That's a really helpful way to think about it. Okay. The material also mentioned thermodynamic potentials. These sound important. What are they?
Yeah, think of them as different ways to frame the energy state of a system, depending on what conditions you're holding constant. They're scalar, extensive quantities.
Like different tools for different jobs.
Exactly. We have internal energy, U, which we've discussed most natural, and entropy and volume are constant. Then there's enthalpy, H, which is U plus PV. Yeah. Super useful for constant pressure processes, like reactions in an open beaker.
H equals U plus PV.
Then Helmholtz free energy, F, which is UTS. That's handy for constant temperature and volume processes.
F equals U minus TS.
And finally, Gibbs free energy, G, which is U plus PVTS, or you could write it as HTS. This one is probably the most chemically relevant for everyday stuff because it's great for processes at constant temperature and pressure.
Right, like most things happening around us.
Exactly. Each potential has its own set of natural variables, the things you hold constant, that make it the easiest way to analyze energy changes under those specific constraints.
So pick the potential that matches your experimental setup.
Got it. Now let's shift to how materials actually behave when temperature changes. You know, it's talked about thermal properties.
Right, when you change the temperature, materials usually change size. That's thermal expansion.
Things get bigger when hot, smaller when cold.
Generally, yes. Linear expansion is about the change in length. Delta L equals alpha L.
Yeah, ALs is the coefficient of linear expansion. It's a material property. LEL is the original length. The LET is the temperature change. Some things expand a lot, like aluminum. Others very little, like fused quartz.
And volume expansion.
Similar idea. ALV, AV, AD0T, where LEL is the coefficient of volume expansion. For many solids, LV is roughly 3 times LL.
So that's why bridges need expansion joints to handle that LEL on hot days.
Exactly. Prevents buckling. A very clear real-world example.
Okay. What about heat capacity? Sounds like how much heat something can hold.
You're on the right track. It's about how much heat energy you need to add to change the temperature by a certain amount.
Okay.
The basic extensive heat capacity, capital C, is just heat added Q divided by temperature change. C, Q. It's simple rail.
But we often specify conditions. Heat capacity at constant volume, CV, can be different from heat capacity at constant pressure, CP. Because if pressure is constant, some energy might go into expansion work.
Ah, makes sense. To make it independent of how much stuff we have, we use intensive heat capacities. Specific heat capacity, lowercase c, is heat capacity per unit mass, usually per kilogram.
Yeah.
C equals Q.
Okay, per kilo.
And molar heat capacity, Cm, is per mole. Cm equals Q and AT. There's also particle heat capacity per particle. They're all related.
Right.
And there's a relation between Cp and Cv too. Cp to Cv plus 2 of each row. Involves expansion coefficient, density, compressibility. Shows how things connect.
Wow. Yeah, everything's linked. The notes mention water has a really high specific heat capacity.
Remarkably high, yes. Compared to metals like lead, copper, iron, or aluminum, water takes a lot more energy to heat up per kilogram per degree.
And that's why oceans moderate climate.
Exactly. They absorb and release huge amounts of heat without massive temperature swings.
Cool. Okay, what about ideal gases? Any special rules for their heat capacity?
Yes. For ideal gases, it connects nicely to degrees of freedom.
Degrees of freedom, like ways the molecules can move.
Precisely. How they store energy. Translation, moving, rotation, spinning, vibration, internal bonds, stretching, bending.
Okay.
At constant volume, the molar heat capacity, CV, D2R, where R is the gas constant.
D over 2 times R.
At constant pressure, CP is D2R plus R. So CP is always greater than CV for an ideal gas.
Because of that expansion work potential.
Right. But for a simple monatomic gas like helium, only 3 translational degrees of freedom exist. So D3, CV, 32R.
Okay.
Diatomic molecules like N2 or O2 can also rotate at 2 degrees, so D5 at normal temps, CV 52R.
And vibration.
Vibration adds 2 more, but only kicks in at higher temperatures. It needs enough thermal energy, like kBT2, to overcome the quantum energy gap for vibration. So at high temps, D7 CV is 72R.
So hotter gases unlock more ways to store energy internally. Neat. Okay, let's dive deeper into entropy again. The microscopic versus macroscopic view. This is where it gets really interesting, right?
Absolutely. Microscopically, statistical mechanics looks at microstates. These are the specific arrangements of all the individual particles, position, momentum, etc.
Like every single atom's details.
Right. A macrostate is what we observe: pressure, volume, temperature. The key is that many, many different microstates can correspond to the same macrostate.
Like different ways to arrange cards that still give you the same hand.
Good analogy. And the fundamental assumption is that all possible microstates are equally likely. Systems naturally tend to evolve towards macrostates that have more corresponding microstates, higher probability states.
More ways for it to happen.
Exactly. Until it reaches the macrostate with the absolute maximum number of microstates. That's equilibrium. And entropy S is defined microscopically by Boltzmann's equation. S equals Kb times log omega.
Yep. PBB is Boltzmann's constant, and A omega is the number of microstates corresponding to that macrostate.
So entropy literally counts the ways the system can be arranged microscopically.
In a logarithmic way, yes. More arrangements, higher entropy. Now, macroscopically for a reversible process, super slow, always near equilibrium, a tiny entropy change ds is just the tiny heat added dq divided by temperature T. ds is dq T.
But for an irreversible process, real-world stuff like rapid expansion, friction, the entropy change is greater than dqt, ds dqt.
Ah, so real processes always generate extra entropy.
Exactly. Which leads to the macroscopic second law. The total entropy of a system plus its surroundings can never decrease. Total is always greater than or equal to zero.
The famous entropy always increases idea.
For the universe as a whole or any isolated system, yeah. It points directionality to time. Some things just don't happen in reverse spontaneously.
Profound stuff. And practical, too. The notes mentioned Kelvin, Planck, and Clausius statements.
Right. Those are different ways of stating the implications. Kelvin Planck basically says you can't build a perfect heat engine, one that just takes heat and turns it all into work in a cycle. Some waste heat is inevitable.
No perpetual motion machines of the second kind.
Precisely. And Clausius says you can't build a refrigerator that just moves heat from cold to hot without any work input. It costs energy to fight the natural flow. And a key consequence. When entropy increases in an irreversible process, an amount of energy, E, becomes unavailable to do useful work. T-min is the lowest temperature involved.
So disorder costs us usable energy.
In a way, yes. The energy is still there, first law, but its quality, its ability to be directed into work, degrades, second law. Every real process makes some energy less useful. That's huge.
Wow, yeah. Okay, switching gears again. States of matter, phases and phase transition.
Right. Solid, liquid, gas, plasma, the main phases. A phase transition is just changing from one to another. Melting, boiling, freezing, condensation.
And energy is involved even if the temperature stays the same during the change.
Absolutely. Internal energy changes. You have to put energy in to melt ice or boil water, even at constant temperature. That energy goes into rearranging molecules, breaking bonds.
That's latent heat, right?
Exactly. Latent heat of fusion, LF for solid liquid. Latent heat of vaporization, LV for liquid gas. It's energy per unit mass.
So the total energy is U equals plus or minus M times L.
Yep. U kill MLF or MLOV. Plus for melting, boiling, minus for freezing, condensing.
Got it. The notes also mention the triple point and critical point.
Yeah, the triple point is a unique temperature and pressure where solid, liquid, and gas can all coexist in equilibrium. For water, it's just above 0 degrees C and at very low pressure.
All three at once.
Yep. The critical point is at much higher T and P. Above it, there's no distinct liquid-gas phase, just a supercritical fluid.
Interesting. And Troughton's rule.
That's an approximate rule, suggesting the entropy change during vaporization is roughly constant for many simple liquids, around 85 gmol/K.
And enthalpy came up again for constant pressure processes.
Right. Since H is U plus PV, the change in enthalpy at constant pressure equals the heat added or removed. It wraps up internal energy change and PV work neatly.
So H positive means heat absorbed.
Yep, endothermic.
Yeah.
H negative means heat released, exothermic. And we define enthalpy of fusion, AGF, MLF, and vaporization, AGV equals MLV. Enthalpy is just a convenient way to track energy in those common constant pressure scenarios.
Makes sense. Okay, let's zoom back into the microscopic. Kinetic theory of gases. What's the core idea?
Kinetic theory explains macroscopic gas behavior based on microscopic particle motion. It uses the ideal gas model. Point particles, elastic collisions, far apart.
The simple model again?
Yep. And for an ideal gas, internal energy U is basically all thermal energy ETH. So changes in U are just NCVT. Depends only on temperature change.
Okay.
A key idea is the equipartition of energy. In equilibrium, energy gets shared equally among all the active degrees of freedom. Each one gets, on average, 12 kBt of energy per particle.
Half kBt per degree of freedom.
Right. And remember, a degree of freedom is active if the thermal energy, kBt2, is much bigger than its quantum energy step. There's also equipartition of space gases tend to spread out evenly.
So temperature really is just average kinetic energy, fundamentally.
For translational motion, yes, the average translational KE of an ideal gas particle is exactly 32 kDT.
3/2 kBT. Okay. What else comes from kinetic theory?
The Maxwell-Boltzmann distribution. That gives the probability of finding a particle with a certain speed. From that, we get the most probable speed, average speed, root mean square speed, all related to temperature and mass.
So not all particles move at the same speed.
Definitely not. There's a whole distribution. Also, Dalton's law for gas mixtures. Total pressure is the sum of the partial pressures each gas would exert alone.
Makes sense.
And of course, the big one, the ideal gas law itself, PV equals NKBT, connects P, V, T, and amount of gas beautifully.
The cornerstone equation.
Pretty much.
Yep.
It explains Boyle's law, PV const, Charles' law, VT const, Avogadro's law, Vn const, Gay-Lussac's law, PT const. All those empirical laws fall out naturally from the kinetic model. It's really elegant.
It really is amazing how those simple assumptions lead to such powerful predictions. Okay, let's talk about how systems change state, thermodynamic processes.
Right. A process is just the path from an initial to a final state. Work done by a gas expanding is W equals integral PdV.
Work is area under the PV curve.
Exactly. And crucially, work depends on the path taken. It's not a state variable. Different path between the same 2 points, different work.
Okay.
For a cycle, where you end up back where you started, the network is the area enclosed by the cycle on the PV diagram.
Clockwise is work out.
Yep, network done with the system. Counterclockwise is network done on the system. And the Carnot cycle is the theoretical gold standard for cycles between two temperatures.
The most efficient possible.
For a reversible engine, yes. It sets the limit. It involves 2 isothermal constant T steps and 2 adiabatic no heat transfer Q0 steps.
Isothermal expansion, adiabatic expansion, isothermal compression, adiabatic compression.
You got it. For any ideal gas process, we know NCVD and the entropy change NCVL NTFTI plus NRLN VFEI.
Okay, those apply generally. What about specific types of processes?
We often look at constrained processes where one variable is constant. Isochoric means constant volume, isobaric constant pressure, P, isothermal constant temperature, T.
And adiabatic?
Adiabatic means no heat transfer, Q0. For an ideal gas, this also means PV to the power of gamma equals constant, where gamma is CPCV. Adiabatic processes are also isentropic constant entropy.
So isochoric, VC, isobaric, PC, isothermal, TC, adiabatic, Q0C, those are the main building blocks.
Exactly. Understanding those helps analyze complex cycles like Carnot.
Okay, let's connect this to real machines. Heat engines, refrigerators, things that run our world.
Definitely. Heat engines convert thermal energy into work. They take heat Q hot from a hot source.
Like burning fuel.
Right. They do some work W and dump waste heat Q cold into a cold sink.
Like the atmosphere.
Often, yes.
Yeah.
Efficiency E is work at divided by heat in. E W Q hot. Since W Q hot Q cold from energy conservation, E equals 1 Q cold Q hot.
Efficiency is 1 minus heat out over heat in.
Yep. And the Carnot cycle gives the maximum possible efficiency between temperatures thought and T cold. E Carnot equals 1 T cold thought. Note. Absolute temperatures, Kelvin.
Ah, crucial point. So you can never reach 100% efficiency unless T cold is absolute 0?
Exactly. That's Carnot's theorem in action. No engine can beat the Carnot efficiency, and all reversible engines between the same T's have that same efficiency. It's a fundamental limit.
A very practical limit. What about Brayton and Otto cycles?
Brayton's cycle is for gas turbines, jet engines. Uses constant pressure heat, addition rejection, and adiabatic compression expansion. Its efficiency depends on pressure or temperature ratios.
Okay, jets. And Otto?
Otto cycle is for typical gasoline internal combustion engines. Uses constant volume heat addition, spark ignition, and rejection, plus adiabatic steps. Its efficiency depends heavily on the compression ratio, V1, V2.
So different engine types use different thermodynamic blueprints. Fascinating. Now, refrigerators, they run backwards, right?
Essentially, yes. They use work input, W, to pump heat from a cold place, Q cold, inside the fridge, to a hot place, Q rack the kitchen.
Moving heat the wrong way.
Right, which requires energy. We measure their performance with the coefficient of performance, COP, often written as K. For a fridge, CREFR equals Q cold W. How much cooling you get for the work you put in.
Q cold over W.
Which is Q cold.
Oh.
Q cut Q cold. The best possible COP is the Carnot refrigerator. K Carnot Treff filters T cold, thought T cold. Again, absolute temps.
Okay. And heat pumps, like for heating a house.
Same principle, just your goal is different. You pump heat Q cold from the cold outside into the warm inside.
Heat cold.
You want the heat delivered Q hot.
Yeah.
So the COP is KHP equals Q hot W.
Q hot over W.
Which is Q hot, Q hot, Q cold. The Cardinal limit is K Cardinal HP equals thought T cold. Notice KHP is always CREF plus 1 for the same device.
Ah, clever. So they all obey the second law by requiring work input to move heat against the gradient.
Perfectly. It all ties back.
Okay, one last major area.
Yeah.
How does heat actually move? The transfer mechanisms. Conduction, convection, evaporation, radiation.
Right. The four ways. Conduction is heat transfer through direct contact. Molecules bumping into each other need a temperature difference.
Like a metal spoon in hot soup.
Exactly. Fourier's law describes it. Heat flow rate H is proportional to the area A, the temperature difference, and the material's thermal conductivity, kappa, and inversely proportional to the thickness, L, H, D, A, T, L.
High kappa means good conductor.
Yeah. Metals have high kappa. Insulators like air or styrofoam have very low kappa. We can also talk about thermal resistance, R equal A. Resistors add in series, like electrical resistors.
Okay, conduction is direct contact. What's convection?
Convection is heat transfer by the movement of fluids, liquids, or gases.
Like boiling water circulating.
That's natural convection, driven by density differences, hot fluid rises, cold sinks. Forced convection uses a fan or pump to move the fluid, like a convection oven or your car's radiator fan.
Ah, okay. Natural versus forced.
It's complex. We use dimensionless numbers like Grashof, Prandtl, Rayleigh, Nusselt numbers to characterize the flow and heat transfer rate. The Nusselt number relates the convective heat transfer to conductive heat transfer.
Got it. Fluid movement, then evaporation.
Evaporation is a phase-change liquid to gas. It takes energy, the latent heat of vaporization. So when liquid evaporates, it cools the surface left behind.
Like sweating cools us down.
Precisely. The fastest molecules escape, leaving lower energy ones behind. The heat transfer rate H is proportional to the rate of mass evaporating, dmdt, and latent heat, LV. Condensation is the reverse gas to liquid releases heat.
Okay. And finally, radiation.
Radiation is heat transfer via electromagnetic waves. Everything above absolute zero emits thermal radiation. No medium required, think heat from the sun.
Light and heat waves.
Infrared radiation, mostly at everyday temperatures. The amount radiated depends strongly on temperature. Stefan Boltzmann law says power radiated H rad equals ST4.
T to the fourth power. Wow.
Yeah, temperature matters a lot. A is area, is the Stefan Boltzmann constant, and epsilon is emissivity, how well the surface radiates compared to a perfect black body.
And black absorbs best, too.
Exactly. Kirchhoff's law says absorptivity equals emissivity at a given wavelength for an object in thermal equilibrium. Black bodies are perfect absorbers and emitters. Planck's law describes the spectrum of radiation, and Wien's law tells you the peak wavelength shifts to shorter wavelengths as temperature increases.
So hot things glow visibly red, then orange, then white.
That's Wien's law in action.
Incredible.
Yeah.
It all fits together. Lastly, a quick note on non-ideal gases. Real life isn't always ideal.
True. Real gases deviate, especially at high pressure or low temperature. The ideal gas assumptions break down. The van der Waals equation is a common correction, adds terms to account for molecule size and attractive forces.
A bit more realistic.
A step closer, yes. There are even more complex models like hard sphere or soft sphere potentials for specific research. But the ideal gas law is a remarkably good starting point for many situations.
Wow. Okay. We have covered an incredible amount of ground here, seriously. From basic definitions of energy, temperature, all the way through laws, potentials, engines, heat transfer.
It's a lot, definitely. Thermodynamics touches everything.
Looking back at all this, what stands out to you? Maybe one or two of the most, surprising or fundamental insights.
I think for me, one is that deep connection between the microscopic randomness, all those jiggling particles and microstates, and the very solid, predictable macroscopic laws we rely on, especially the second law. How statistics at the tiny scale leads to inescapable rules at our scale. That's pretty profound.
The emergence of order, or at least rules, from chaos.
Sort of, yeah. And maybe the other is just how strict that second law limit is on efficiency. That Carnot limit, 1T Coulthard. Even a perfect engine can't get 100% unless you have absolute zero to dump heat into. It's humbling.
Absolutely fascinating. It really gives you a deeper appreciation for, well, everything. Everyday stuff, the tech we use. I know I'll be looking at my cooling coffee very differently now.
Yeah.
And for you, the listener, I really encourage you to keep an eye out for this stuff day to day. Notice how heat moves, why your drink cools down, why rubbing your hands warms them up. Think about efficiency. It's everywhere.
It really is.
And maybe a final thought to chew on. Considering that second law, the arrow of time, this unavoidable increase in entropy, is perfect energy efficiency truly impossible? Or could there be breakthroughs, maybe things we haven't even conceived of that might let us, well, bend the rules somehow?
That is a provocative question. What does the future hold?
Exactly. Something to ponder. The universe according to thermodynamics. It's a deep and fascinating place.
Couldn't agree more. Always more to explore.